let's do a physics problem. Electrodynamics, chapter 6. This is problem number 12 from this book. Okay, so the basic idea is that there is a infinitely long cylinder with a permanent magnetization inside of there. We want to find the magnetic field everywhere, two different ways. First, what we're going to do is to find the bound surface current and volume current density and use that to find the magnetic field. And then we will use the H field and Ampere's law to find the magnetic field. We're going to use Ampere's law either way, but let's just get into it. So we have this magnetization in the z direction, and it has some function k, s, z hat. So here we're using, I'm going to use what the book did because it's the book. So s is the cylindrical coordinate distance from the z-axis instead of r. I like r, but they use s, so I'm going to use s. And so the first thing we want to do is to find the current density J, the bound current density J, and the bound surface current density KB, and then the second way we'll do it with the displacement field. So let's just get into it. We want to find JB first, so I'm going to say the bound current density JB is the curl of the magnetization. So that's just something that we know from before. Now I also want to say I'm going to do this numerically. You know I do things numerically too, which is a little iffy, but it's going to be fun. We're going to have a great time. I promise you everything's going to be great. So I need to take the curl of this. Now this is in really cylindrical coordinates is the right thing to use here. So I need to take the curl in cylindrical coordinates. So let's do that. JB, I don't remember this, so I'm going to write it down. The nice thing about this book is in the front cover. I need to mark my spot because I don't want to lose my page there. In the front cover, you have all your vector identities. So it says curl in cylindrical coordinates, right down here, curl. You see it? Okay, so I'm gonna write that out. I need to take this off. So I'm gonna write it out. The curl in cylindrical coordinates, it's going to be 1 over s, and that's that r value, partial of mz with respect to phi. So remember, we have the coordinates here. I'll draw my little coordinate system here. That's z. This is going to be s, and then the xz, the angle is phi right there. Okay, so I have that minus, oh, I lost it already, minus the partial of m phi with respect to z, right, s hat, plus the partial of ms with respect to z minus the partial of mz with respect to s, right? Phi hat, and then I'll wrap it around, plus 1 over s, the partial with respect to s of s times m phi, and this is pointless because most of these terms are 0. We already know that. Minus the partial of ms with respect to phi, z hat. Okay, so if we do these derivatives, so remember right up here, I have m only has a z component. So I have a ms is kz, all the others are 0. So mz with respect to phi, what's that going to be? Well, there's no phi term in there, so that's 0. M phi, there is no m phi. Ms with respect to z, that's 0, right? There is no z value in that. Mz, there is no ms. I don't have an s component. Mz with respect to s. Well, now that I do have, right? So I'm going to get a negative k, and then that's going to be in the phi hat direction. And then down here, I have m phi. There is no m phi term. I have ms. There is no ms term. So I get that. So that is my volume current density. So JB is going to be equal to negative k phi hat. So that's going to be, if you were going to draw that, right? So this is my z direction. So I'm going to get, that's my positive phi direction. I drew that wrong. Yeah, I did that right. So this will be negative phi direction. So if I look at this, it's going to be coming out like that. And it's constant current density, okay? And then on the other side, it's going to be going in. That's right, constant current. I did that right, right? Yep, got it. Okay. So we have that. Now we need to find the surface current density. So the surface current density, KB, is going to be equal to m cross n hat. So n hat is a unit vector perpendicular to the surface. So right over here, we have n hat going this way. It's n hat's going that way. So, and really, we're going to do m cross s hat. Well, let's just go ahead and do this cross product, m cross s hat. And remember, s hat, I'm using that direction. I'm going to use my normal cross product rules, but I'm going to use s hat, phi hat, z hat, and then I'm going to put my components of m. Well, I only have a z component. So it's 0, 0, ks. And then I'm going to put my unit vector for s hat. So it's going to be 1, 0, 0. Now I can actually do the cross product. M cross s hat. And that's going to be equal to expand about the s hat. I get 0, 0, so 0 s hat. Expand about the phi hat. I'm going to get negative, no, I'm going to get positive ks, ks, and then 0, so ks phi hat. And then I'm going to get z hat, I get 0, 0. Now, this is the surface current density, so I actually have to evaluate this at s equals r. Right? I'm at the surface. S is not anything. It's at r. So this is going to be equal to k r phi hat. Notice it's in the opposite direction up here. So on this surface current, it's going to be going in the into the page. So it'll be like this. This is k. And then over here will be coming out. OK. So these two things are important. KB is k r phi hat. Now, you could use some symmetry here. You could say, OK, this looks like a solenoid, and we already did that problem. But I don't want to do that. Let's just go ahead and use these current densities to find the magnetic field. The first thing is we have to make an argument, right? So let's just take any solenoid. And we did this before. This is like a solenoid with solenoids inside of it. Now, the total current may not be 0, but we can still look at the total magnetic fields. So over here, imagine I have a bunch of wires. Let's just take these outer wires. So if I cut this in half, the current's going into the board right there, going out of the board right there. So each of these wires right here are going to make a magnetic field in the direction like this. So it's going to make a magnetic field going down that way and up that way. And these over here are going to make a magnetic field going up this way and down that way. Now, but also, let's go ahead and add in, this is going to make a magnetic field going up that way. I should draw these all different colors. Let's do that. Let's put these as orange. And let's put these as yellow. So the orange ones are going to make magnetic fields going down, up, up. And these are going to make ones going up, up, down. So you can see inside of the cylinder, the magnetic fields add together. Outside, they're in opposite directions. Outside, they're in opposite directions. Now, because we have a very long wire, because they're very long, these don't really change as you get further away. So they actually do exactly cancel on the outside. So the magnetic field on the outside is 0. The magnetic field on the inside is in the positive z direction. And that's kind of a conceptual argument, right? Okay. But now we can use Ampere's law to find that magnetic field on the inside. So let's do that. So I'm going to erase this stuff. And so we know, I'm going to go ahead and write this. B is B z hat. I know it's in the z hat direction. I've just said that. If you want to use Ampere's law, you have to utilize the symmetry of the situation. We have to. Okay. So now let's just say, here's the center. And suppose I pick a path that looks like this. And so this is a distance s away, and this has a length L. Well, I can integrate B dot dl around that path, because Ampere's law says the integral of B dot dl around that path, that's a dl, is mu naught I in. Well, I can integrate. Let's go this way around that path. So B dot dl around this path is going to be B times L, because they're in the same direction, and B is constant. B along that path, yes, there is some B right here, but it's perpendicular to the path. So B dot dl is going to be 0. Over here, the magnetic field is 0, so that's going to be 0. And then right here, it's perpendicular again, so that's 0. So now what we need to do is to find the current passing through this whole area right there. We have a current density right there, and we have a surface current right there. So here I get BL is going to be equal to mu naught times. Now, in order to find the total current passing through that area, I'm going to need to integrate over the current density. So this is going to be the integral of J dot n hat dA. That's the current passing through that. And in this case, n hat is a unit vector in the perpendicular to my area. The way I pick this, that unit vector is actually going to be phi hat. And then I have to find the current through here. That's just going to be equal to the current density KB times L. Okay, so let's do that integral right there. The integral of J dot phi hat dA. So notice that J is in the phi hat direction. So I actually get negative K times the integral of dA. And so dA is actually going to be equal to it's going to be L ds, right? So we can break this into tiny little pieces like that. Each piece has a length of ds, and then I can integrate. So that's not too difficult to do. I get negative KL times S from S to R. I shouldn't have done that, but that's fine. So if I integrate it at the limits, it's going to be negative KL R minus S. So now if I put this all together, I get BL is mu naught times this integral right here, which is negative KL R minus S. And then I have that plus KB. KB is KR, K. That's the constant K times R times L. Now I can divide both sides by L. The L's all cancel. And I get B is negative mu naught KR plus mu naught KS plus mu naught KR. So that cancels, and I get the magnitude of the magnetic field is mu naught KS on the inside. And remember, we already said it's in the z direction, so now I can write this as B mu naught KS z hat. So that's my magnetic field on the inside. Let's put that over here, and let's put it in a different color. Bn is going to be mu naught KS z hat. Okay, so we found JB, we found K, and we found the magnetic field. Now let's use the H field to do the problem again. So recall that we defined the H field, or the auxiliary field, or whatever you want to call it, as B over mu naught. Is it minus M or plus M? Why did I just forget that? Minus. And Ampere's law looks like this. The curl of H is equal to I free, J free, the free current density. And we can write that as an integral. The integral of H dot dl is equal to I free. and that passes through that. So that's our, it is Ampere's law. Okay, it just uses H instead of B. It's still Ampere's law. Well, if I again I have no free current density. There's no free current density. So that means that the integral of H dot dl is equal to 0. No, it's just a scalar. Well, how can that be except if H is equal to 0? So we have H equals 0, both inside and outside. So now I can go outside and I can say H outside is equal to B over mu naught minus M, which is B over mu naught minus 0. The magnetization outside of the cylinder is 0. There is nothing there. There is no magnetization. So if that's true and H is 0 and B minus mu naught minus 0 is 0, so the only solution is B out is 0. That's what we got before. Now let's find it on the inside. On the inside, B over mu naught minus M equals 0 vector. So I can solve for B. B is mu naught M. And I go back up here to M, I get K S z hat. So I have mu naught K S z hat. Identical, same thing. So which way is better? I mean, it depends if you even care about those current densities, the bound current densities. I think this way kind of like makes a little bit more sense. Remember, why do we use the H field? And we use the H field so we don't have to, we can kind of solve the problem independent of the material and then apply the material later. That's why it's there. Okay, you know I can't leave it at that. You know I have to do this in Python. And it's going to be fun. I think it's going to be fun. We want to see if we get the same magnetic field here. And what I'm going to do differently is if I know the magnetization, the magnetization is equal to the magnetic dipole moment per unit volume. So can I make a cylinder with a bunch of magnetic dipoles and then calculate the magnetic field using the magnetic field due to a dipole and just do it for all of those dipoles, sum it up. So I'm actually going to call this dB, the magnetic field due to one dipole is mu naught over 4 pi 3 m dot r hat minus m, times r hat, minus m over r cubed. So if I want to find the magnetic field right there, I need to find this vector r, I need to find that magnetic field due to that one, and then that one, and that one, and that one. So there's a bunch of stuff I got to do here. I mean, the first is this. This is not trivial, right? So how do I find that? Well, what I'm going to do is make a cylinder. I'll make a bunch of random points inside that cylinder in a Cartesian distribution. So I can say dV is going to be the total volume divided by the total number of pieces. And then I can find the magnetization M is going to be equal to, that's lowercase m, M dV, and that's going to be equal to K S dV z hat, so in the z direction. And I'm going to do it in the z direction, even though I would like to do it in the y direction for VPython, because it looks a bit better. But then that will be my dipole moment for each one. And so that you see the more dipoles I put in there, the smaller this thing is going to be. So it's going to change the dipole moment. And then we can calculate the magnetic field inside and see if we get the same thing as what we have over here. Let's just jump into it. Okay? Let's just, no point wasting around time when we could just jump into it. And so we're going to jump into it. And here we are in VPython. And I already have it started. But we have to pick some values here. So let's just say mu naught is equal to 1, just because it's easier. And then I'm going to say r equals 0.2. I'm just picking a value. I do need I can't make an infinitely long cylinder. So let's say L is equal to 10 times R. I don't know. That seems fine. And then I need a value for K. Let's say 0.1. Again, I'm just picking things. Let's see, what other constants do I need? That's it. So let's just make our cylinder to see what it looks like. I'm just going to make a cylinder. Now, so in WebVPython, a cylinder has the property, the position property is the start of the cylinder, and then the axis goes from the start to the other thing. So let's do this in the z direction. It's not going to be super pretty, but it's going to be 0, 0, negative L over 2 is the position. And then the axis is going to be equal to vector 0, 0, L. And then I need the radius is equal to R. And then I'm going to make it transparent. Opacity equals 0.2. POS is not defined. POS equals. POS must be a vector. Okay. Oh, vector. I don't know what I'm thinking. Okay, so there's my cylinder, and it's in the z, so the z direction is in and out of the board. I think that's fine. Okay, and so it's clear. Next, I want to go ahead and make a bunch of points, and I want to put them in the cylinder. Okay, so let's generate a bunch of points. N equals, let's say 500, N equals 0. While n less than n. I'm gonna add them to a list. So let's go ahead and make that list. MS. That's the dipole moments is plural. So I want to generate a vector. RT is going to be. I want it to go from negative R to R and negative L to L. Is that right? That's what I want to do. No, I'm just going to go negative L to L. That's what I'm going to do. Okay. So I'm going to say half an L. Yeah, I'm going to go from negative L to L. So this is what it's going to look like. 0.5 times L times the vector 2 times random minus 1, 2 times random minus 1, 2 times random minus 1. So random gives you a number between 0 and 1. 2 times random, 0 to 2. Minus 1, I get a number between negative 1 and 1. And then I multiply it by L. So I'm going to get a box that goes from L to L to L. Why is that 1/2 there? Let's see. Let's just run this. So once I make that, I'm going to draw a sphere there. So let's just put a sphere there. Sphere. POS equals RT, radius equals, let's say, R over 50. And then let's add 1 to my counter. N equals N plus 1. Let's just see what that looks like. Okay, so there's my stuff. Yes, I'm going, this is negative. This is L over 2 to L over 2. That's why I did the 0.5. So it's in a box, right? But what I want to do is to limit them into the cylinder. Let's make these a little bit bigger so you can see them a little bit better. Yeah, so now I want to also limit them inside the cylinder. So what I'm going to do is to calculate what I call Rxy. This is what you would call it S in cylindrical coordinates. This is going to be the square root of RT dot x squared plus RT dot y squared. It's the distance from the z-axis. And then what I'm going to do is to say if the Rxy is a scalar, Rxy is less than R, then put the sphere there. So I'm going to copy this, cut this, put it right here, oops, put it in there, and then and only then will I count. So now all the points should be in the cylinder. So they're all in there, still 500. I didn't count them unless I did that. So that's good. Now what we want to do is to make that magnetization arrow. So I'm going to add arrows to the list, and all my things are going to be arrows. And I don't really need to do that, but I'm going to do it anyway. So I'm going to turn this off, and then instead of making a sphere, I'm going to say ms equals ms plus an arrow. The position is going to be RT. The axis, let's put up here m scale. We don't really need this, equals 1. The axis is going to be equal to my, it's going to be m scale times, let's go up here and call this mi, the dipole moment. I'm going to go ahead and calculate the dipole moment. It is equal to k times s. Is that right? K times s, right? So it's going to be k times s, which is going to be rxy, times the vector 0, 0, 1. That's the same thing, right? So now this is just going to be mi. And then I'm going to add a property to this arrow called mt. mt equals mi. So now I can refer to that later on. I can refer to the dipole moment for each one. But they're going to be arrows, and it should display them as arrows, but the size might be off. We don't even need them, but let's just do it anyway. Okay, so there we go. There we have all our arrows. Let's make them a little bit bigger, scale of 4, just so we can see. Okay, and you can see, especially looking down the barrel here, that the ones that are closer into the center are smaller, right? Because as S increases, they get bigger. So I'm pretty happy with that. That's my magnetization cylinder right there. Now what we need to do is to create a function that calculates the magnetic field at any particular observation location. So let's do that. Def, I'll call it BM ROT. So this passes some observation location ROT, and it's going to return the magnetic field due to all of those dipole moments. So I'm going to set up a temporary vector to start with, because you can add something to 0, but you can't add something to nothing. Okay, so now I can go through my list of dipole moments, calculate the r vector, and then calculate the magnetic field due to that one and add it to the total. So let's say for mt, I'll use that mt, mm and ms. So mm is going to be each individual dipole moment. R is going to be ROT minus mm.pos, right? That's the vector from that particular dipole to where I want to find the magnetic field. And then dB is the magnetic field due to that one dipole moment. So this is going to be equal to mu naught divided by 4 times pi times 3 times dot product of, let's make another one up here, r hat is equal to norm r, just so I don't have to type it. So it's going to be dot mt, right? That's that dipole moment, and r hat times r hat minus dot mt, and all of that divided by mag r cubed. And now I'm going to add that to the total. BT equals BT plus dB. And then I'm going to return BT. So let's just go ahead and put the observation location RO. This is called RO. It's going to be, let's put it outside the cylinder. So let's put it at vector 2 times R 0, 0. Let's just see what happens. If I print it out, print BMRO. That's just to see if things are working. Okay, so does this mean anything? It's hard to tell. It is in the z direction, right? That is important. We like that. We only have 500 dipoles too. Did I calculate? I didn't even calculate dV. I put down m total. So if you're watching this and you saw my mistake earlier, then I apologize. So dV is going to be equal to pi times r squared times L. L divided by N. And then this is going to be equal to, I have to multiply this by dV. And so that's going to make it a lot smaller. And you'll notice you can't even see the dipole moments anymore. And that's fine. I don't really care. I already saw that they're working. And down here, I get some super small number. And so that seems like it should be okay. Should be okay. Okay. I don't have an infinitely long cylinder, and it's fine. Okay. So now what we want to do is to make a graph of the magnetic field from 0 to, let's say, 1.5 R. So let's do that. So down here, I'm just going to do it down here. let's make a graph. G1 equals graph. Let's say x title equals R, y title equals BZ, and let's put the width 400, height 200. And then I'm going to make two graphs. F1 equals G curve, color equals color dot blue, and this is going to be label equals BN for numerical, and then F2 equals G curve, color equals color dot red, label equals BT. For the theoretical, we already calculated what that should be. So I'm going to go over here and say x equals 0, dx equals 0.01. That's my step size. I'm going to move my x value from x equals 0 to, let's say, 1.5 times r. So while x is less than 1.5 times r, do the following. I want to calculate the magnetic field. So let's just make an observation location. RO is going to be the vector x0, 0. And then I'm going to calculate B, but I'm going to go ahead and plot it. So F1 dot plot x versus the, let's do the z direction. BM of RO dot z. That's in the z direction. And now we're going to calculate the theoretical. So I'm going to say, I'm just going to go ahead and plot it. Plot x. And then the theoretical magnetic field is mu naught k x. So it's mu naught times k times x. Now I need to increase my value of x. X equals x plus dx. This is going to look bad. Okay, we're going to fix it though. Okay, so this is my theoretical and this is my actual. So we have a couple problems. Number one, we don't have an infinitely long cylinder. Number two, I only have 500 points, right? That's not that many. And then there's another thing that's going to come up in a second. So let's just go ahead and increase my number of points. If you can do 500, you can do 5,000. There's no difference. Okay, so it looks a little. Oh, you know what? One thing too. I said that if I need to fix that because outside the cylinder, the magnetic field should be 0 theoretically. So up here, I'll just say if x less than r, then I'm going to plot that. Else, spell it right, else f2 dot plot x0. Okay, so it's still not looking great. One of the things that can happen is you get these spikes appear, and but it does drop down to 0. That's kind of nice. These spikes are due to getting too close to a magnetic dipole moment. So remember, the dipole magnetic field goes as 1 over r cubed. So if I get too close, that magnetic field to that one dipole is going to be too important. So let's make a minimum distance. I'm going to call this r min. And it's just going to be, let's say, the cube root of dv. So it's going to be dv to the 1/3. That's my distance scale. And if I get closer than that, then I don't want to calculate that magnetic field. So down here, when I calculate this, I calculate dB, but I'm going to say if the distance r, which I already have, if mag r is less than r min, no, if it's greater than that, then I'm going to add it to the total magnetic field. Otherwise, I'm just going to ignore it. And that's just to prevent these explosions. Okay, so that did not work. Let's just turn this off. Oh, min. That's why. So you can see here that it gets a little bit better. I'm maybe cutting off too many pieces. One thing I do want to do is to, you could increase the number. I think I'm going to stop here because You can play around with this some more. The idea is the important thing. It does increase, it does drop to 0, that's good. It doesn't completely match up. I don't want to go greater than 5,000 because I'm drawing them. You don't have to draw them. You could do this without drawing them. And then you could go to 50,000 and it should work just fine. And then the one thing you want to play around with this, what's that R minimum distance? You can try changing it up to different things. So there you go. I'll put a link to this code down below. The first part of the problem is just theoretical and it's from the book. And this is just extra stuff. I think that's fun though. Okay, I'll talk to you later.